Hey y'all, here's the systems unit test review. Going over it with you guys so that you have a great study guide to study with and bring back to class the next day. So we are starting at the end actually. We're going to start by graphing systems of linear inequalities. Remember, the solution to a system of linear inequalities, which means two linear inequalities, is in the double shaded region, but not on a dashed line. Doesn't matter which line is dashed, it cannot be on that dashed line, but it has to be in the double shaded region, the one where the two colors overlap. Now, if we wanted to do this example problem, to graph the line, we would need a slope and a y-intercept for the first one. Here's a slope and here's the y-intercept. Based on that symbol, I know that this is going to be a dashed line shaded above. So I'd begin at 5. And I'd create more points by going down 1 over 3. And again, down 1 over 3. Until I felt confident that I could draw a straight but dashed line through these points. So here I go with my ruler, making sure I'm making an actual dashed line through the points. Awesome. And shaded above. Now for the next one, it is not in y equals format. So before that I can do any of the graphing, I'm going to need to solve for y. It means I take the 3x to the other side. This would leave me with negative 5y less than or equal to negative 3x minus 20. Divide by negative 5 everywhere, but my inner spidey senses should be going off because when I divide by a negative number, I need to flip-flop that inequality sign. It goes from being less than or equal to greater than or equal to. Which means that I have a slope of 3/5 and a y-intercept of 4, but I know that this line is going to be solid and above. I begin at 4, and my slope is up 3 over 5. 1, 2, 3, 1, 2, 3, 4, 5. Now I'd run out of room if I kept going to the right, so instead of up and to the right, I can go down and to the left. Double negative means positive. 1, 2, 3, 1, 2, 3, 4, 5. And this time when I put my ruler down and draw my line, I make it an actual solid line. Pew. But this one is also shaded above. So we have created essentially 4 regions on this graph, but my solution set is where the shading overlaps. So where the red and blue overlapped is the region with all of my solutions in them. Now, specifically, looking at the next question here, it says list 3 solutions to this system. A solution would have to be in the super shade, so we could do this point right here, which is 0, 7. We could do this point right here, which is 2, 7. Or we could be so crazy as go to like 5, 10. 5, 10 would be in my super shade if I were to graph it. Now, if I'm looking at things that are not in the solution set, things that are not in the solution set, 0, 0, not in a double shaded region. This coordinate right here, 5, 5, not in the super shade. It's in one shade, but it's not both. And if I looked for the coordinate 0, 5, that's on a dashed line. So that is not a solution to the system. And in fact, that's one of my tricky non-solutions. Okay, a tricky non-solution would be 0, 5 because it's on a dashed line. Looks like it's in the solution set because it is where both lines or both shading is overcrossed, but that dot itself is on a dashed line, so we cannot count it as a solution. On the next page, we're going to go to graphing just regular inequalities, which if you could graph the beginning, you got these. Remember, again, a solution set for a linear equality, not a system, is just in a singularly shaded region, but still not on that dashed line. Okay, let's fill in the types of lines here. For less than, that's a dashed line. For greater than, that's a dashed line. For less than or equal to, that's solid. Greater than or equal to is solid. If I'm looking at the shading, less than is lower. So less than or equal to is also lower. Greater than is bigger. Bigger numbers are above on number lines. So we're going to be graphing or shading above. Those are the 4 things you have to have memorized. Dash solid above or below. So if we were graphing this linear inequality, this time we'd have a slope of 1/4 and a y-intercept of -1, and based on the symbol, this would be dashed and below. I would begin at -1, go up 1 over 4, up 1 over 4, until I could draw a super confident dashed line between these points with my ruler. Not my best dashed line, but you guys get the idea. Wow, really not a good dashed line. Sorry. But we do want to shade in below for dashed and below. So that means my solution set is this half plane where it is shaded in, where all of the coordinate points in there are solutions. Now again, remember the dashed line does not count. So the coordinate 0, -1, which was my y-intercept, would not be a solution. Now, we're going to go back a little bit. Something we learned at the beginning of the 6 weeks, writing systems of equations from word problems. 3 steps to writing a system of equations are as follows. Read the question. Probably want to do this like twice, but read the question. We are going to define our variables, which means we're going to list out what they represent. And then we're going to organize our information into 2 equations. Now, in Algebra 2, you might have 3 or 4 equations, but in Algebra 1, we're going to stick to having 2 equations each time. The 3 forms you may see, or you might write, is slope-intercept form, which is y equals mx plus b, where m is the slope, but in words you might see per, each, every, which means we're going to be multiplying that number by x, or by one of the variables. If you're writing it and you have a b, that's the y-intercept, but in words you might see initial value, or flat fee, or one-time fee, something that's happening only once. It's my initial value, or what I'm starting with. The next type of equation you might see is standard form, which based on your formula chart is ax plus by equals c, where you just have to pick the a, b, and c numbers. Now, when we're organizing this information into 2 equations, you got to make sure you keep money plus money equals money. Item plus item equals items. Look at the labels. What are they labeled? They need to go together. And then if you have a total equation, like the total number of nickels and dimes, you just add up x and y. And the third type of equation is our other. And so why does thinking of a balance scale, I'm moving my arms and you can't see me, like the balance scale help with these questions? In your own words, you can answer this, but basically we're going to want to make sure that what we know, whatever is heavier or lighter, gets balanced back out when we're writing our equations. Equations mean that they are equal, so they have to weigh the same. So we use our arms like a balance. I'll draw the balance scale here so y'all know what I'm talking about. This thing, where we got to weigh some, so one would go down, you'd have to add something here so it weighed the same. So for example, it says Academy sells right-handed and left-handed baseball gloves. Last month, 12 gloves were sold for a total of $561. Right-handed gloves cost $45 each, and left-handed gloves cost $52 each. Write a system of equations that best models R, the number of right-handed gloves, and L, the number of left-handed gloves that this Academy sold. So R is right hand, and L is going to be left hand. If we go back and reread this question, we'd see that we sold 12 gloves, and then for a total amount of money, and then we have money numbers to go with each of the right-handed and left-handed gloves. Okay, well, if we keep that idea together, $45 for every right-handed glove. Oh, sorry, we're not using X, we're using R. And $52 for each left-handed glove, that's an L, for a grand total of $561. All of these are my dollar sign numbers. Now, the dollar signs won't be in your answer choices, but if you want to write them there to help you remember why you put those together, that's great. Then we know that we had a total of 12 gloves sold, so a total is just adding up the variables together, setting it equal to that total. There's my system. Now, if we're writing linear inequalities from the word problems, all of those steps are the same. However, you're going to be needing to find one of these other translations for your inequality signs. Is more than is the greater than symbol. Is less than is the less than symbol. Is no less than is greater than or equal to, because it's not less than, which means it has to be greater or equal. And no more than is less than or equal to. These two are the one you're going to see the most. They're the most common in real life, specifically this one, no more than, because it has to do with budget management. No more than having a maximum budget. So when we would write these equations, you're just going to be looking for these translations, these down here, because it would let you know which inequality sign you actually want to put in your answer. Now, if we want to solve systems of equations by graphing, and remember about our special systems, there's a couple steps here. This is more steps than we wrote down in our notes, but I really want to make sure you have all the steps for yourselves. You got to make sure when we're graphing a system of equations, okay, graphing to find the solution, we write the equations in slope-intercept form, which again is mx plus b. We identify the slope, which is my rise over run. Tells me exactly how to move across the graph. And we identify the y-intercept, which is the coordinate point on the y-axis. This is where we begin. So we begin at the y-intercept, move with the slope, repeat for the second equation. So you're going to repeat steps 1 through 4 for both the first and second equation that they give you. Then we find the solution, which is the point of intersection. And we can check our answer either using Desmos, a calculator, plugging in our coordinates to both systems. There's plenty of ways to check your answer here. Okay, so here we go. We're going to graph it. On this first one, we have a slope of 2 and a y-intercept of 2. Now, if I had a slope of 2, remember that's 2 over 1, which is my rise and my right number, rise and run. So we start at positive 2 on the y-axis, and to create more points, I'd go up 2 over 1, up 2 over 1, up 2 over 1, until I could confidently put my ruler down and make a super duper good straight line. Let's see how I do today. Not bad. All right, make sure it extends all the way across your graph, Miss Quigley. You're right. And we're done with the first one. The second one, however, is not solved for y. So instead of using the intercepts to graph this, which I totally could do, I'm just going to go ahead and solve this for y. So I move the 3x to the other side using inverse operations. These don't combine together, so I just write them down next to each other. We divide by negative 4 everywhere. If this was an inequality, you would have flipped the sign, but it's just an equation, so it doesn't really matter. 3 divided by 4 is 3/4. 12 divided by negative 4 is negative 3, which means now I have my slope and my y-intercept. I begin at negative 3, and I'm going to create more points by going up 3 over 4. Up 3 over 4. It's kind of off the graph here. Can't click it because I have a toolbar in the way. So I'm going to make one in the other direction. 1, 2, 3, 1, 2, 3, 4. Then I grab my ruler and I make a super duper good straight line. Come on, Miss Quigley, you can do it. Ooh, that was not great. I'm going to try that again. My ruler slipped. That's much better. And I know that this system has one solution because it crosses one time. And I would be able to say that that solution is the coordinate negative 4, comma, negative 6. Negative 4, negative 6. Coordinates are always x, comma, y. So I got to look at the x-axis, then the y-axis to create that coordinate. I could check this in Desmos. I could type in both of the slope-intercept form equations to Desmos test mode, and it would show me where they cross. So I can always check my work. Now, talking about the special types of solutions we have, we just did one of these where there was one solution. Check. They cross once. But does anyone remember what happens when the lines are parallel? Well, they don't cross, so we would literally answer that they have no solution because there's at no place that they are the same. This is if we were solving by substitution or elimination when we'd get a random equation that said this. Does 0 equal negative 8? No, 0 does not equal negative 8, which means we have a wrong number there. It's no solution. If they happen to be right on top of each other, substitution elimination would give me something like 0 equals 0, which is true, and we would answer infinitely many solutions, or IMS, because they are always crossing, so they have infinitely many number of points that they cross. Last two things you're going to be asked to do on this test is to solve a system by substitution. The steps for substitution are here for you on your review, as well as the steps for elimination. Okay, they're the shortened steps, and they're not an example for you, but I want you to be able to use it. When we're solving by substitution, the first thing we need to do is isolate a variable. I'm going to take this equation and isolate it, which means I'm going to add 6x to both sides, because that will get the y all the way by itself. This would be y equal to 11 plus 6x. This is isolated, so now I can plug this equation into the other one. Okay, I started off with negative 4x plus 2 times y, but instead of y, I want to put 11 plus 6x, since that's what I have isolated for the y. I solve. Solving takes 2 steps. We're going to distribute negative 4x plus 22 plus 12x. I'm distributing, which is multiplying, equal to 14. Use inverse operations or the box method to start solving. I'm not going to show you those steps. You guys can do it. Subtract 22 from both sides. That's negative 8. We divide by 8. And either using inverse operations or the box method, you'd get that the solution is negative 1. Now that's half of the answer. Remember, once we get here, we want to substitute the value back into the equation. So I'm going to use the isolated equation that I started with, but instead of x, instead of 11 plus 6x, I'm going to plug in that negative 1. Well, 11 plus 6 times negative 1 is like 11 minus 6, which is 5. So I know that my y is 5, which means my final answer, my solution to this system, is negative 1 comma 5. I can take this x and y value and plug them back into the equations so that I can make sure that they give me true statements, which means it's a solution. Elimination has similar yet different steps. The first thing we're going to do is look for an opposite like term. I don't see them. Neither of those are opposite like terms, but if I multiply this entire equation by negative 2, this would be the same 2x plus 8y equal to 6. Then I'd get negative 2x minus 8y equal to negative 6. The next step says to add the equation, so I'm going to pretend like this is a good old-fashioned addition problem. And hopefully you notice that all of them turned out to be opposite like terms when I did that multiplying by negative 2. So I would end up with an equation that said 0 equals 0. Based on what we said about the types of equations we can get, this would actually be an infinitely many solutions answer, because that is a true statement. True statements means infinitely many solutions. If I had been able to continue to solve this, I would have plugged in numbers very similar to like what I did with substitution. You solve, you substitute a value, and you end up with a coordinate pair. Hopefully this helps you guys. Really study hard for this unit test. I think we're all fully capable of getting the grade that we desire on it. Have a great day, y'all. Bye.